let's get going, shall we? Welcome all. So today's Darwin Day. I should have probably figured out how many days it has been since Darwin was born, but some time. I think things have moved on, things have evolved since then. Today, I thought, there's lots of things that could be said about evolution, but, in the world today, I think it's a nice thing sometimes to think about how we evolve kindness, which is a trait like any other, and it's actually something that really threw a spanner in the works of the whole theory of evolution. So what we're going to do today is just have a kind of tour through some of the kind of cool evidence and ways of thinking and links between maths and biology that help us to explore and think about the evolution of kindness. Now, there's a ridiculous number of people here who I've taught before. Hello. But for those of you who I haven't taught before, my name's Paul. Hi. I'm a kind of bit of a mathematician, bit of a biologist nowadays. That's fine. There's a whole design flaw with this theatre that, if people come in late, you kind of have to point in line. I've taught lots of you in one guise or another, but actually one of the first people who I taught in this room is my co-presenter today, Andrew, who I taught many years ago, first year mathematical biology.
Indeed.
Yeah. Indeed. And like many people, I think Andrew came up as a first year thinking, why do biologists need all this maths malarkey? And so I'm hoping that since then he has seen the light. And
working on it.
Well, yeah. So he has done many awesome things since then. So in fact, he was a PhD student here until relatively recently in Christ.
Yeah.
So some of the MCR people you may have met at some point, I don't know. We're going to talk about sociability. We'll see how sociable Andrew was. So he was one of my first mathematical biology students many years ago. So you've got him to blame for me still doing this, those of you who have had mathematical biology inflicted on them by me. And we're going to be kind of kicking off, I think, Andrew, just giving you a little bit about why Darwin and what Darwin thought.
Yeah, thanks, Paul. It's really lovely to be here. I want to start off with a bit of a famous puzzle in the history of evolutionary biology. So Darwin discovered natural selection in 1838. Now, I don't know about you, but if I just discovered natural selection, I'd want to publish that pretty quickly. But those of you in the room who are good Darwinians, what year did The Origin of Species come out? 1859, absolutely right. And again, before any pedants jump in, yes, I know technically the Royal Society paper was 1858, but the bigger point here is that he's waited nearly 20 years to publish. That's a very long time. Some of you are probably under 20, so he's waited almost your entire lifetime to publish this incredibly groundbreaking theory. There are many reasons why, and we're only going to focus on one. And this was that some traits were really hard for Darwin to explain. I don't want anything that follows to give the impression that Darwin didn't crack these puzzles by himself. It's true that for all these puzzles he didn't get all the way to the correct answer, but he was an incredibly hard worker. Most of those 20 years were spent with him doing endless experiments. His wife complained that he was one of the worst husbands to have because there were frogs' eggs stuck to the wall, there were pigeons being selectively bred in the attic. It sounded like a pretty crazy place to grow up. But one of his biggest mysteries was this. If you've been watching TV recently, you'll know, of course, about faithful and traitors. And for Darwin, he would have been interested in who's the traitor. For him, the biggest mystery was the faithful. And what's so odd about ants, bees and wasps? What's so weird? Any ideas? What's the big mystery?
Just faithful to the Queen?
Yeah, absolutely faithful to the Queen. And it's a form of faithfulness which seems the very one thing that natural selection could never create. And that's that most workers are sterile. And Darwin very cogently realised this is a big problem. If natural selection is a process of reproductive competition, how could a billion-year process of reproductive competition yield individuals who never reproduce. This, it seems like if there's one thing natural selection couldn't make, and certainly shouldn't make, it's that. So don't take my word for it. He called it the most serious special difficulty my theory has encountered. Now, we've often heard of ants, bees and wasps, but before we start talking about cooperation, I do want to show you another big puzzle which foxed Darwin in terms of being kind. Has anyone been here or know what this is in the City of London? So it looks like some sort of kind of renovated public toilet or nondescript bus shelter, but it's actually a really, really lovely place. It's the Memorial to Heroic Self-Sacrifice. So it was built in the 1900s to commemorate ordinary people who died giving their lives to others, and maybe some of you can start to see the link. This memorial, it's a set of tablets. You can see some of the tablets there. If we zoom in, we can just get a quick glimpse into some of these sort of rarely known stories. So this lady here, a steamship went down near the coast of Guernsey, and she sacrificed her life by giving up her lifebelt, but allowing others to live. She went down with the ship. One of the tablets even has a Cambridge connection. John Cranmer Cambridge, a son of the city who gave his life saving a drowning boy. Unfortunately, the memorial, there was originally plans for 120 tablets. They sort of ran out of steam. There were disputes over which pottery company they were going to use, and it sort of fizzled out. But excitingly, in the last decade, new tablets have started to be added. So this was a tablet added in 2007. And so if you do go to the memorial now, they've got some really cool QR codes and apps. You can read about these people and their stories. Well, what's the link to Darwin? You can probably imagine Darwin was confused by this sort of level of self-sacrifice he commonly saw in human societies. He said, well, we might praise noble people, we might build memorials for them, but anyone who sacrifices their life for another, who lays down their life for a comrade, would leave no offspring behind to inherit their noble nature. Now that's all very well and good, but if any of you have studied evolution and behaviour or other evolutionary modules here, you've probably already heard of ants, bees and wasps. You've probably already heard about the idea of behavioural cooperation. But what we want to think about today is, might Darwin have actually missed an even bigger cooperative mystery? Might there be something on Earth which is far, far bigger in scale in terms of cooperation and in terms of sort of weirdness in evolutionary terms than just a few bees in a beehive or a few people nicely helping drowning little children? Any guesses what that might be? What might the biggest instance of cooperation on Earth be? Any imaginative guesses? Go for it.
Multicellularity.
Absolutely right. The answer was staring Darwin in the mirror. When he was writing his book, he himself was a bigger cooperative society than any of the bees, ants or wasps he was puzzling over. So just in case you're not familiar, what is multicellularity? Well, in biology, all cellular life is either unicellular, a single cell, such as bacteria, archaea, not a Swedish furniture store, but a group of extremophile single-celled organisms and some fungi, like yeast. Or it's multicellular. Each organism contains more than one cell, such as plants, animals and fungi. And just to put some numbers on this, if you do a sort of guesstimate of the total number of honeybees, the same animals that Darwin spent many decades puzzling over, how many honeybees are there in the world, you get something in the sort of order of magnitude range of 10 to the 12. But if you then do the same estimation process, the same sort of Fermi problem for how many cells in your own body, just in one person, in Darwin alone, there are at least an order of magnitude more cells working together. So he's the real enigma here. And just before I hand over to Paul, again, just for some of you, if you are non-biologists, what do we mean by a multicellular organism being cooperative? Well, just in the same way as in worker and queen bees, you have the ultimate sacrifice being made of non-reproduction. If you look in your own bodies, of course, the vast, vast, vast majority of your cells do not reproduce. They are an evolutionary dead end. We call them somatic cells, be it neurons, muscles, skin cells, any cell, really, any cell apart from a gamete, apart from a sperm and an egg. And it's a big sacrifice to make. Those DNA molecules, they have descended from a line of winners. Every single, all of your ancestors were successful. in the process of reproduction, and they're the first time there's been a loss. Those DNA molecules have, if you like, voluntarily decided to not reproduce and to dedicate their lives to helping the germ cells, helping the gametes, the sperm and the eggs. This mirrors almost directly the same puzzle that Darwin thought about in worker bees and the queen. All I've done there is change the word cell to worker or queen. It's exactly the same logical puzzle. It's a similar puzzle to the puzzle of the sort of memorial of the faithful. Why can, or how could, a process of reproductive competition lead to some individuals voluntarily giving up that right? And I think now Paul's going to talk about some of the mathematics behind how we might make predictions about this.
No, yeah, I think, is it decisions first?
Yeah, absolutely, I can do those. Apologies. So, it's obviously a planned interlude, just to show you that nature isn't harmonious and that there are conflicts. Deep level of thought's gone into all of this. Apologies, one more bit. Just to put some numbers on these sacrifices, again, to try and impress you, and just make you think that actually this is sort of honeybees on steroids. That's what you all are, as a multicellular organism. So what sort of sacrifices are your body cells asked to make? Well, they're asked to stop dividing, but I think most people don't appreciate just how few cells in your body can actually divide. So over 99% of the cells in your body now have made the ultimate sacrifice. Almost all terminally differentiated cells cannot divide. In your average tissue, less than 1% of cells are stem cells. And of course, even those stem cells, vast majority won't go on to form gametes. What else might an example be of a sacrifice that body cells are asked to make? Any other dramatic cases where we might ask them to do something for the good of the whole? Yeah. Yes, I'll go for you, but absolutely right. We use slightly less direct language. We'll say self-destruct and apoptose, but I agree conceptually they are. That's 50 to 70 billion cells a day receive that order. Self-destruct. And again, for the last 3.8 billion years, none of their ancestors have followed that directive. They've not self-destructed, they've reproduced. That's an incredible sort of ask to make. Also, we ask them to not over-consume resources. And you might think, well, that's silly because the body controls the allocation of resources. But what can a cell do to get more resources for itself? Any ideas? Well, it's a good idea. Absolutely right. In cancerous cells, what they do is they release angiogenic signals which say, hello, local blood supply, I would like some more. Can I please have some more vascular tissue formed to me and steal resources? That's what tumours do. Angiogenesis, the formation of new blood vessels, cheating, essentially, opposite of cooperation, is the first hallmark of aggressive tumours. Just one example, you might have seen this in people. What's the one place in your body where your cells are supplied by oxygen directly from the air rather than from a blood vessel? And it is, yeah.
Cornea.
Absolutely right. And if you injure your cornea, then you'll see a temporary growth of blood vessels in. They'll give enough oxygen and glucose to repair that tissue, and then it'll go away. So normally, again, this blood vessel behaviour is very well behaved. But given this potential to cheat, and given that you've got 13 trillion cells at any one time, and many more over the course of a lifetime, we now need to think about when would cells be expected to cheat. And I think now it's time for
Go
Go back, absolutely. Yeah.
Right. So I did ask Andrew to make sure who was a fun guy during this session, but he said there wasn't much room.
I don't do jokes. No jokes. Don't worry. Yeah. Yeah. Oh, sorry.
So I've been asked not to put too much maths in, but I couldn't help myself.
Yeah.
So
no chance.
I'd like to get a theoretical framework going for how we can think about natural selection and prove it. So this is a cool rule, especially just put in for all my economists who've turned up, yay, to say, well, what is a kind of theoretical mathematical framework for evolution? So we're going to imagine two generations, an old generation and a new generation. And there's going to be some trait in that generation. And we're going to try and make this as general as possible, so that what does this trait mean? It could mean all sorts of things. It could be the length of your hair, or the number of cells in your body, or your kindness, or all sorts of things. Anything that can be measured in any abstract way, even if it's really difficult to measure. And we've got a whole load of individuals. We're going to label the subscript I, because I am an individual. And then we're going to look at the probability of individuals of this type being there in the old generation and the new generation. So, it's quite hard what do we mean by evolution almost? What do we mean by change in these things? These are things that Darwin was seeing and observing, but how do you, as a mathematical model, create something that describes it? Well, sometimes we make maths look really complicated, and sometimes we have to keep it kind of simple and just say, well, the evolution is just a change in the trait. So sometimes it can be more trait, sometimes less trait. If there's more trait, maybe it's a traitor. So the change in the average values, they're not going to get any better. Those of you who've been taught by me know that they're not going to get any better. The average change in Z, well, I think most people here have done either some kind of economics-y, maths-y, mathematical biology or things like that. So this is, I've got quite a lot of expectations of you on these slides. So the change in Z here is just the expected value of Z in the new regime minus the expected value of Z in the old regime. Okay, that isn't too bad. And
it's not changed.
And then it hasn't changed. Then, what's happened here? Well, all I've done is add on nothing. But I've added on a very special type of nothing, a very complicated looking nothing, those two middle terms. And, this is the kind of thing that we do in maths all the time, is just, so you've probably had lots of questions asking you to simplify things. In advanced maths, we often have to complicate things before we make them simpler. So, so I've now just added on these two terms. So subtracted this and added this, so I haven't changed the expression. But now some things kind of just want to be together. So I'm going to pair up those first two terms because there's a common factor of the sum of pi. And if we do that sum, then this becomes the sum of this pi dashed multiplied by the change in z plus the other junk there. Okay, where's this going? So we need to introduce something that's going to have the effect of talking about how fit the individuals are. Survival of the fittest and all that. So what might be our way of defining how successful an individual is? Well, it's going to be to do with how the probability of being that type of individual in one generation changes in the next generation. So again, well, we can think about that a little bit and just say the new probability is just going to equal like the old probability scaled by this thing called fitness, which is this WI. And for reasons that become apparent later, turn into WI as a ratio WI out of the average fitness, W bar. So if I just substitute that in here, we get that the change in Z is now this horrible thing. Okay, where's that going? So I'm going to multiply through by W bar. Now, we've got a sum of some probability times something. Sum of a probability times something is just the expected value of that thing. Okay, that's kind of nice. This is the sum of the probability of something. Well, that's also just the expected value of that thing. And this is the average value of W multiplied by this sum of pi zi, that's just the average value of zi, the average value of z. So this is an expected value of W times the change in z. this is the expected value of of w times z minus the expected value of w times the expected value of z. Those of you who've been doing some economics or stats recently, what is the expected value of AB minus the expected value of A multiplied by expected value of B? Whoa. Some of you need to get a new supervisor. So this is the expected value of W times the change in the trait, plus what we call the covariance of the fitness with the trait. Well, we're just in a whole load of algebra. Nobody loves algebra. I'm a bit too obsessed with algebra. My wife's really worried. She thinks I'm totally obsessed with my ex. So we've got all this algebra, but there's no point in it unless we can interpret it somehow. So what does this actually mean? Well, this term here is to do with like the expected value of the change in z in isolation. So maybe there's just some external thing that's changing z. Is that kind of, so what might that be? Maybe, I don't know, there's an improved type of apple being found, and now all your horses are just a little bit bigger because everyone's eating nicer apples. There's no selection pressure there. That's just things changing as the environment changes. So this is often called the environmental term. What about this then? What does that say? So those of you who have been doing a bit of linear regression might know that this idea of covariance, how much one thing varies with respect to another, that's to do with like correlation and regression and lines of best fit. So you can start, maths is all about making links. I should probably mention that at some point. And this is all about, how does one impact on the other? Well, what's that term? This is saying that your change in Z overall is, there's some like background environmental thing changing Z, and there's also the Z changes depending upon how much your fitness changes compared with Z. We've just proved natural selection. So this covariance term can be analysed in lots of different ways using different linear regression models, but all of natural selection is embedded within this idea that if we want things to change, if we want things to evolve, then we need there to be some covariance. In fact, what we can do, if we really wanted to, is say this Zi, this could be any trait we like. Well, that trait could be fitness. So we could just set our Zi to be equal to Wi, and then what's the covariance of a variable with itself? Yeah, that's just the variance. So this is saying that if we want to increase our fitness, if we want to change our fitness, that can't happen unless, well, there can be some external source, but that's quite difficult to do. But generally, if we want to increase our fitness, we need there to be variation. So variability is vital within biology. Sometimes that can be hard to explain. Why, if there's like a really good thing for animals to do, why don't they all do the same thing? And this is saying that if you don't have variability, then you will never have improvement. Which is kind of cool. So this gives us all sorts of interesting theoretical ways to start thinking about evolution. So now the problem becomes, how can we describe this variance? Why is it that some things improve fitness and other things don't? And once we can understand that, then we can really get into evolution. So, we're going to, this is a really cool little animation that we're going to look at, looking at how might trust evolve. And this is a very, very famous experiment. So, let's play a game. This is called the game of trust. So you've got a machine. If you put a coin in the machine, the other player gets 3 coins and vice versa. You can either choose to cooperate, put in a coin, in which case you put in a coin and your opponent gets 3 coins, or you can cheat and just not do anything. What do you want to do? Cooperate or cheat? Hands up. I don't believe in democracy necessarily, but we're going to do that. So hands up for cheat. Hands up for cooperate. Oh, such a nice group. We'll have to do something about that. So if you cooperate and they cheat, you lose a coin when they gain 3. However, if you both cheat, you neither gain anything or lose anything. So actually, if you analyse this, this is a topic of maths called game theory, where based upon this, actually the sensible thing to do is cheat. Because if you cheat, you have an expected gain. If the other player cooperates, what should you do? Yeah. You want to cheat. That's mean, but also the correct answer.
How often do we do this game?
Well, trust is nice, but it can let others take advantage. You should shoot as if you're in a war. Sometimes distrust is rational. But now what happens if we play the game more than once? So this is called an iterated version of the game. So what are we going to do? So we've analysed it, so what should we do first? Yeah, let's cheat. Now what should we do? Ooh. Now what should we do?
Cooperate.
Oh. Now? Okay, we've got a new opponent. What should we do? Oh. Now what? Let's try cooperating. Well, I wonder if we cooperate again. We don't appear to be doing very well. Let's go back to cheating. Oh no, we've got a new opponent. Oh, she looks friendly. What should we do? Cheat. Okay, let's cheat. Okay, cowboy, what should we do? Okay, let's try cooperate. Oh! What should we do? Let's try cooperating again. I've had enough of cooperating. Ooh, what happened there? Okay, let's try cheating. Now let's be nice. Oh dear. So I would, this is called the evolution of trust, I would recommend you go and try playing some of this. So our total score on that was 33. The lowest possible score is 7. You'd like to know? The highest possible score is 49. So who were these people that we just played against? So there's Copycat, who starts with cooperate and afterwards I just copy whatever you did in the last round. There's Always Cheat, the strong shall eat the weak. Always Cooperate, let's be best friends. There's the Grudger, I'll start by cooperating, but if you ever cheat, I'll cheat you back forever. And then there's the Detective, first I analyse you, I start with cooperate, cheat, cooperate, cooperate. If you cheat back, I'll act like a copycat. If you never cheat, I'll act like you always cheat. So, what happens if these people play against each other? So who do you think is going to get the highest score? Place your bets. So there's going to be 10 pair matches, 10 rounds per match. Who's going to win out? So we've got all these people playing against each other. Who's going to win? Okay, hands up for copycat. Okay, some for copycat. Hands up for always cooperate. Hands up for always cheat. Hands up for grudger. And hands up for detective. Oh, let's see if it's detective. That does seem to be popular. Let's go. So we keep playing and playing and playing. And if we do that many, many times, the winner was copycat. So just doing whatever the person did to you before seems to be a really good idea. So that's what happens if you do it all just once. But what happens if you do it many, many times? So we're going to do some evolution now. So we're going to play a tournament, eliminate the losers, and reproduce the winners. So, who do we think is going to win in this? The cooperates, the cheats, or the copycats? The copycats did well last time. Let's try that. So eliminate the bottom 5. Bye-bye cheats. Reproduce the top 5. Oh, the always cheats seem to be doing well. So now the always cooperates are dead. But if there's no one for the cheaters to take advantage of, go copycats. And this occurs again, even if we put like other types in. And this is what, there are international tournaments where we play repeated games against people. And copycat seems to do really, really well. But there's a problem. If copycat is always happening like this, then, well, how can trust evolve? So far, we've just learnt about players who are always playing like this. So how can trust and distrust happen? So copycat seems to do really rather well. But what happens if you change these parameters? So what happens if, like, cheating gives you more of an advantage and the like? We can play with that, but I'm just going to go through. But the key to understanding trust is one big weakness of copycat. Imagine 2 copycats playing against each other. They're nice, so they're going to cooperate. Let's see what happens. Oh, that was good. So let's do it again. Oh no! The copycat fell over. So this is what might happen if there's kind of an error or miscommunication. So then the opposition thinks that they cheated, so he will cheat. But then the copycat has to retaliate. So if only there were things that could deal with mistakes. So there are all sorts of other things which we can talk about here and different simulations. And I'll let you go away and play with some of these and see if you can understand why some of them might be a good idea. But we're going to get back to a little bit of this. So I'd like to look at some game theory here. Could you? Just in a kind of general context of these somatic cells. So if you're a cell, you know that you're going to be going up against some other cells. And maybe your other cell's going to be cooperative or your other cell's going to cheat. So if you're a cooperative cell, if you're going in a population with other cooperative cells, well, this is what we call the payoff. So this is how much, in some units or other, the cell gets if a cell goes up against a cooperative cell or a cheating cell goes up against a cooperative cell. So we need to decide, are there any conditions when cooperation is a good idea? So imagine that you're this is what we call evolutionary stable states. You're going up against a system where everyone else is playing as a cooperative cell. Under what conditions should you also be cooperative? If you know that most other people in your system are cooperative, should you be cooperative if A is less than C or A is bigger than C? So you've got a choice of these two. You know that the cells, you're in some tissue with other cooperative cells. You want to know if you want to be cooperative, what's the condition for you to be cooperative? Yeah, you want A to be bigger than C. That says, well, I'm better off playing the cooperative strategy when I know that other people are going to be cooperative. And this is what we call synergism. So this cooperation is stable. If everyone else is cooperative, you should be cooperative too. And a cheat won't be able to invade that. So a cheat has a disadvantage. It's got less payoff when you choose to cheat when everyone else is being cooperative. If A is less than C, then that's unstable because if there is a cheat, they have an advantage. And they'll be able to come in and go, oh, look at all these lovely cooperative cells who are doing lots of useful things for me. What about B less than D? So if B is less than D, what does that mean? It means that if you're in a system where all the other cells are cheating, then do you want to be cooperative? No. You're wanting, if everyone else is cheating and you're cooperative, you're just going to be taken advantage of if B is less than D. But if B is bigger than D, then all those cheats are just like beating each other up and you can be like, I'm a lovely person and everyone's going to love me because they will trust me and bring me gifts and do lovely things. So there are times when even if everyone else is cheating, you should choose to be cooperative. And that condition is that D is bigger than B. So we need these two things to happen for multicellularity to occur. We want the cooperation to be better than being selfish, so B is less bigger than D, and we don't want cheats to prosper in this cooperative paradise. So we don't want them to be able to invade. So shall we?
Yep. Well, I won't even try to compete on the jokes front. That was amazing. So look, what we'll do now is Paul's done this amazing sort of mathematical theoretical analysis, and now we'll do the one thing that mathematicians often don't tend to do, is go and actually test it and see if it's relevant at all to biology. But I think hopefully there'll be some good synergisms, and we will find that it is. First prediction: the idea that we should only get multicellularity if cooperation was favoured. I mean, this seems almost obvious. We're sort of saying multicellularity would only occur if it was good for it to occur. But we do still need to test it. Now, I like to imagine this is Darwin's birthday. What might Darwin say if he'd have just heard this analysis? Well, I think he would have been really impressed and blown away. But then when we said, could you test it? he might have been a little bit more sceptical. Well, why might Darwin have been a bit down and a bit pessimistic about the idea of testing this? Well, Darwin unfortunately believed, and really sort of laid the groundwork for the common public belief now, that evolution is very, very, very what? When you say evolution to most people think it's very, very slow. So don't read the whole quote, just look at the bit in bold. The idea that of all these wonderful evolutionary changes, we can't see them. In some ways, you could be a cynic and say, well, isn't that convenient? But that was one of the reasons he delayed for 20 years, because he was so determined to try and find observations from living things which only made sense if they had evolved, because of the fact that he thought you couldn't see them. And I think for most people, when I said, oh, my PhD was on evolution and on modern evolution, they think, well, how? We think evolution is really slow, so it's gradual, you can't even see it. We have this, and they're not wrong in a way. Evolution does take place on a billion-year timescale. Just to sort of hammer Darwin's point home before we look at a potential solution, I always really like to get a grasp of Earth's kind of deep time by using the analogy of the 24-hour clock. So when you look at that, strange clock, 24-hour clock, built for Henry VIII in Hampton Court Palace. In this analogy, we imagine that Earth's history begins at sort of 0000, and that the present day is 2400 hours. Any guesses at which point on the clock life begins? Roughly, how long do we have to wait?
Half an hour.
Well, it's a good guess. I was just about to say, anyone who answers will almost certainly be wrong, so it's just good to have a guess. So don't worry, no question. About 4 a.m. Okay, we get our earliest fossils go back to about 5:30 in the morning. But here's the real question. How long do you then have to wait from the evolution of life at 4 a.m. to the first animals and plants? Yeah. Again, you've all got intuitions in your head. I won't make you say them. About 8:30 to 9:30 in the evening. You can see where this is going. Well, actually, the dinosaurs were not on Earth at sort of 2 in the afternoon. You've got to wait until pretty late. You've got to stay up late. Dinosaurs come onto the scene properly about 20 to 11, going extinct at 20 to midnight. What am I going to put up next? Humans, absolutely right. Humans come onto the scene. Obviously, it's the centre of the universe with only 19 seconds before close of business. So we can sort of see why it was very reasonable for Darwin and for many other people to think today, well, nice ideas, but we can't really test these evolutionary hypotheses because it's such a slow process. Do a quick group poll. How long did the evolution of multicellularity take? You've got 4 options. 1,000 years, 10,000 years, 100,000 years, or 1,000,000 years. Just curious to sort of poll the sense in the room. What do we think? Votes for 1,000 years. Maybe we should do this. Votes first of all for I've got no idea.
Can we just be clear? Yeah. This is from single cells.
Yeah, sorry, apologies. This is from unicellular to multicellular. How long did that transition occur? Votes for 1,000 years. Fine, we'll take it about 2. Votes for 10,000 years. Okay, slightly more. 100,000 years. 1,000,000 years. Okay, well you're all wrong. What about this? What about less than a year? Well, what I want to do now is run through some really cool experimental work that's been done relatively recently, looking at this question and looking if we can leverage this to then test the ideas about when we should see it evolve. What's that? Any ideas? What sort of life is that? Any guesses? It is a cell, yeah. Oh, and it is an algae, yeah. It's not. Sorry, yeah. You said clammy. It is Chlamydomonas. Yes, well done. So we're going to look at Chlamydomonas. Now you might think it's quite a boring little organism, but it is really, really easy to keep in the lab. And imagine if I gave you what sounds like an impossible project. I said, I want you to try and evolve this unicellular alga into a multicellular one, and you're not allowed to cheat and use CRISPR. You can't do any sort of fancy gene editing. Given what Paul's just said about the idea that cooperation will evolve when it outweighs cheating, what could you maybe do, or what would you have to try and change to stimulate its evolution into multicellularity? Well, you'd have to somehow make it better to be multicellular than unicellular. We'd have to manipulate the environment such that being cooperative, i.e. being multicellular, was better than being a selfish unicellular loner. So, how can you do that? Well, you might start to come up with very sort of complex manipulations you can do. Just for time, I'll give you the very, very boring and almost looking overly simple mechanism they used. So what's going on? In this experiment, they set up 8 Petri dishes, each Petri dish containing thousands of this single-celled Chlamydomonas. And it's very important you understand that in nature, this species is always single-celled. It doesn't have any sort of facultative multicellular state. It's always single-celled from life till, well, throughout all its life. In 5 dishes, they then added a predator. This predator is called Paramycium. Here's Paramycium, also single-celled. It's a predator of algae. How could it eat an alga? Well, would you like to watch a video of Paramycium gobbling up some algae? Yes, of course you would. So, sick people. Paramycium, it beats its cilia to waft the algae into what's why call it a mouth and you call it an oral groove. That's Paramycium's oral groove. Here's a video of Paramycium gobbling up some algae. So probably the revolution in grace, but you can see its cilia sort of beating as it wafts about, gobbling up some algae. Question: why might adding a predator make multicellularity beneficial? And the answer here, it will sound silly, but any guesses? Go on, yeah?
The bigger you are, the harder it is for you to be engulfed.
Yes, and now I'm going to translate that into sort of language you see in the paper. Might multicellular individuals be too big to fit into the oral groove? So, there you go. But, you're absolutely right. You're absolutely right. You know, it's essentially saying here, well, look, you know, you can eat things bigger than your mouth because you have teeth. Paramycium doesn't have teeth. Therefore, if the algae could evolve to be too big to fit into the oral groove, then perhaps multicellularity would spread. If cooperation is better than being selfish, it should happen. So, okay, we've got these 5 dishes with the predator. They ran the experiment for only 50 weeks. Again, under traditional thinking, you know, you should just see nothing because it takes millions of years and there's nothing you can do. What do they find? Oh, and I should say as well, why have we got 3 dishes without the predator? They are a control, absolutely right, just to check there's nothing sort of weird going on about being in a Petri dish, which, you know, could be increased density or something. Okay, so what do we find? In the 3 control dishes, no change. So, started unicellular, still unicellular. In 3 of the dishes containing the predator and the algae, again, no change. But in 2 of them, excitingly, a new multicellular form had evolved. This would be the best birthday present for Darwin, if he wasn't, you know, sort of in the grave for the last year. But still, someone go and tell him. So, just to show you, because it's really beautiful. So what you've got here, this is a 3-panel figure. On the left panel shows you the normal life cycle of Chlamydomonas. I spend my whole life as a single cell, and then I have this one like tiny brief phase of meiosis, and then I split into 4 little cells which go off and repeat the cycle. B and C here. B is dish 1 that evolved multicellularity. C is dish 2. And I hope you can see that actually in both dishes it was a different form of multicellularity that evolved. It was a different way of being multicellular. I saw that now. So what's our conclusion? You know, if B is bigger than D, as Paul said, multicellularity can evolve very rapidly in less than a year. Just a few quick questions. Why don't you think you saw all of the dishes evolve multicellularity? Why did 3 not? Any guesses? Maybe. Yeah, it's good guesses. It's good guesses, but there is another. Yeah.
Is it just like a lack of variation?
Yeah, absolutely right. Probably, our most parsimonious explanation, just the right mutation didn't occur. That also explains why we get different forms of multicellularity. Same predator. There are many routes to multicellularity. One more question. It's actually really easy to turn a unicellular species into a multicellular one. Which genes would you have to mutate? What function would they have to have normally in a cell? And if you break those, you're sort of guaranteed to get a multicellular species. Genes which are involved in... I think people whispering it. These are the C. Again, here we're the same thing. Yes, cytokinesis. Absolutely right. If you go through mitosis, you divide your nucleus, but then a protein which is normally going to kind of finish cytokinesis breaks down, Well, your cells are stuck together. Just before I hand back to Paul for a few more bits, this has been replicated many, many times in many, many systems, and in some cases we've sort of gone to the next step. So rather than just seeing little multicellular blobs, we've seen sort of the next stages of multicellular complexity. What's that? Any ideas? Yeast, yes, well done. In this study here, so they used gravitational selection to stimulate yeast to evolve multicellularity. Now that's a bit like the oral groove. What do you think gravitational selection is? Yeah, it's waiting for them to fall to the bottom. So they spun them around, centrifuged them lots and lots of times, kept repeatedly selecting those at the bottom. Well, multicellular individuals will sink more because they're heavier. So if I keep repeating this, I actually quickly get unicellular species evolving to multicellular ones. But why is that so cool? It's so cool because when these multicellular yeast evolved, what they, and I hope not in a sort of politically charged naming called snowflake yeast, evolved. These snowflake yeast, I think they're pretty robust actually. These snowflake yeast, they started to evolve to do certain things which normally we associate with complex multicellular life. For example, they waited until a certain size until reproducing. What do we say about an animal's life cycle if it does this? We say an animal's life cycle has... Absolutely right, a juvenile stage and an adult stage. What was even cooler is that actually when they started working out which snowflakes did better and which snowflakes did worse, well, the snowflakes that did best produced smaller daughter clusters. So rather than just splitting equally in half, they'd bud off with little snowflakes, which sort of matches what we see animals do. You know, when an animal reproduces, it doesn't split in half, it leads to smaller individuals. Why? Because you can get more offspring. But what a snowflakey sounding tune, that's lovely. Very light and fluffy ringtone. But the question is how? How could you get your snowflakes to break unequally in half? And this is the beautiful bit, this is the big wow moment. You all need to go wow in a second, I'll tell you when. How could you make the snowflakes do this? Well, maybe if you had some cells who were willing to act as weak links in the snowflake structure so that it could snap unequally, i.e. some cells evolved to sacrifice themselves. We have germ soma divisions in our snowflake yeast. Apoptotic cells evolved that formed a weak link in the cluster, evolving soma and germline cells in the lab. Now you go, wow. But will this newfound cooperation be stable in the long term? And now it's back to Paul to try and convince you all that actually it's probably a more miserable future than what we've just seen.
Nothing personal.
Yeah. So, we all know it's good to work together, but that's kind of the easy bit. Having situations where B bigger than D produces some evolution, that's no problem at all, really. But how do we stop cheats prospering? That's a much harder problem, because, have any of you ever been taken advantage of? So, yeah, cheats can often get this free ride. So, do you know what these are? These are E. coli. And there are two different strains of E. coli. Don't they look lovely? I'm sure their mother's very proud. So there's a cooperator strain, and this produces an antibiotic resistant protein which benefits all those around it, so it sends out some lovely antibiotics. And there's a cheap strain, which just sits in the lovely antibiotic soup that the other ones have produced, and just takes advantage without those metabolic costs. So, what will happen if we put some of these together? So, in the absence of antibiotics, the cheats are going to have a competitive advantage. But when antibiotics advantage is added, the cheat frequency kind of goes down. So this is what happens, but notice that the antibiotics don't kill the cheats off to zero. So they need a certain number of cooperators around to act as a lovely, friendly shield to protect them from these antibiotics. In the absence of antibiotics, they do really well. So you get this stable, low-frequency deceit. Again, this feels like relationship advice. So, is this inevitable? What happens if we allow a population of 100% cooperators to evolve? So we just put all these lovely, friendly people in a room together. What's going to happen? Cheating. So, after just 2 weeks, if you have these friendly E. coli all in a petri dish and just leave them, eventually there will be some that just turn off the plasmid that creates this antibiotic, and they'll just be like, why do I need this? Other people are doing this for me. Let's just stop. So in about half of the lines, half of the petri dishes, we see this type of behavior. So is that inevitable? Well, there's this idea of negative frequency selection. So it's good to be rare. Just as I was saying before, I mean, this comes back to the idea of variance being good for evolution. We need there to be variation. We want there to be some rare things. It's generally quite a good thing. So what's going to happen if we start off with a few cheetahs there? They'll exploit things, so the cheetahs do really well, and the cheetah population grows. The cheating becomes less advantageous because then there are just other cheats around. So then we need some antibiotic coming from somewhere. So then the cheating becomes less common, and the cooperators become dominant, and then the cheetahs and you can see this cycle. Cycles are very, very important in biology. This is a lizard. So this is a lovely little lizard from America. And what do you notice about these three lizards? They're different colours. So there's an orange lizard, a blue lizard, and a yellow lizard. And as well as having different colours, these genes are associated with different behaviours. So the orange lizard is large and aggressive. It'll have a harem of lots of females that it defends. The blue lizard is intermediate. It can look after one woman at a time. And the yellow lizard is small and weak, has no territory, and sneaks matings by impersonating females. So, which of these strategies is the best? Well, if you've got lots of orange lizards, who do you think is going to do well if one other lizard tries to attack a group of lots of orange lizards or tries to invade? Yeah, yellow is going to do really well because there are these big territories with lots of females, and you can just go in and sneak in and be like, oh, another female, and then quickly mate. What about who's going to beat up the blues? Yeah, orange will beat up the blues because if you've just got one female and someone else comes in and they're bigger and stronger and have lots of females, then that's going to do really well. And then, what do you think about the relationship between blues and yellows? If there are lots of yellows, then these blues will just come in and be like, hey, I can look after my woman. You can all go away and I'll be all, I don't know, there's a lot of masculinity going on. I don't know. So, we've got these three, and each of them beat another. What? Does that remind you of anything? They're playing rock, paper, scissors. And a biologist monitored the frequency of these, and as predicted, these frequencies cycle. So just like the previous one, we can create a payoff matrix, and those of you who have done mathematical biology recently, or for some of you this is just going to be coming up in a few weeks, we can turn these payoff matrices into differential equations. Do you know which differential equations they turn into? Lotka-Volterra. So those of you who've done a bit of mathematical biology recently, there's a set of differential equations that cycle round just like this. These frequencies cycle. Is just a game of rock, paper, scissors. and the strategies are fittest when rare. So, and if we look back, it hasn't just been happening over the last 100 years. These cycles have been going on for millions and millions of years. And so we've got this idea of game theory where someone coming in and kind of cheating and doing something that's advantageous for themselves seems to be a really good thing. So why isn't it happening in our bodies? How can cheating be prevented? So for multicellular organisms to survive, one possibility is to get rid of cheats entirely. How do we do that? The cheater's advantage isn't going to go away. So there must be another way. And that other way is to ensure that there are no cheaters to begin with at all. How do multicellular organisms lock out cheaters? How might that happen? Kian?
Can you punish any cheaters?
I mean, there will be, in any evolving system, there will be some cheaters that occur, and a lot of our anti-cancer systems are about detecting these cheaters and getting rid of them. So it's true that we have some systems to eliminate them, but how could we lock them out from the beginning of the process? What is the beginning of the process? So one aspect of animal reproduction is really, really strange. This is a blue whale. It's got about 10 to the 16 cells in. That, for those of you who aren't aware, that's a large number of cells. And then when it reproduces, so it's putting a huge amount of energy in getting all these cells fine-tuned and working and created and connected together. Then when it reproduces, how many cells does it use to reproduce? 1. So it's taken all these cells, which will probably include some cheating cells in there, and then it strips them all away and says, let's just choose one cell. And if that cell's a cheater cell, then that embryo is not going to do very well, because just a small number of cheaters don't tend to do very well. So this is a way of encouraging things to start off honest, at least. So there are all sorts of different networks that we could think about how multicellular organisms develop. So it could start from a single honest one, and then just build and build and build, and if there's some cheating occurring, it kind of gets rid of some of those branches and does some pruning. And that is how things tend to develop. So what other possibilities are there? Well, we could have aggregate multicellularity, where there are just lots of cells from different places in the whale that come together and create a new little mini whale. And we could do that, but then there's a danger that some of those cells will be naughty cells. And then we would create a bad whale. Or we could have some kind of budding process where a multicellular animal just kind of splits up into 2 multicellular animals. But then there'll be almost guaranteed to be some kind of cheating cells in there. And in a large population there will be a small number of cheating cells. So just this idea of this single cell bottleneck, it's kind of hard to explain until you think about what is the evolutionary advantage of this, and it's stopping cheating. So the possibility of cheats piggybacking is just much, much higher if you've got this large multicellular group. So stripping it back to 1 is a great way of getting rid of this cheating problem. Let's switch back.
Yeah, and I would just say before I talk about cheating or cooperation, how is it that when I stand up here and show you that germline soma divisions can evolve in the lab, I have to tell you to say wow? All Paul needs to do is say lox of Volterra, and everyone just gasps. It's ridiculous. So clearly rigged audience. But yes, just to say, I mean, I think it's incredibly interesting, and also how we see exactly the same analogies in social insect colonies. Social insect colonies, you might have sort of 10 to the 5, 10 to the 4 workers in some of the big ones, but they'll still go back to a single mated pair to start a new one. again with this idea that we're locking out cheats before they can even arise. So just as we conclude, I think it's fun to think, if Darwin was in the audience now, it's his birthday, what might he say? And to be honest, I'd be pretty worried because he wasn't someone to hold back. Have a look at this quote from his diary. We've all had days like that. There are actually many Darwin quotes. Usually his diary where he writes, if I see another peacock's tail, I'm going to vomit, I'm sick of it. That's a genuine quote. I think he also might feel that he got a bit of a bad rap at the start, because we were showing he was so puzzled by these social insects, and he was, but his solution was actually pretty close to the modern concept of inclusive fitness theory. The same with the people self-sacrifice, and again, he raised the problem, but some of his solutions about the idea of, on average, you might acquire reputational benefits, and it just needs to be good on average to be seen to cooperate. Well, we now know that human cooperators are in general more attractive than those known to be cheaters. So we're not trying to convince you that Darwin didn't think about these problems. But I do really, really hope that he'd have enjoyed listening to the fact, that biology is often seen as a subject where there's a lot to remember and not a lot to think about. But that actually when you apply maths and a bit of logical thinking, you can solve these big problems like multicellularity. In other words, what I hope Darwin would say is, if it was in the audience, I hope he'd say, I agree. I think biology is all about making links. And and I enjoy the fact that you can link together the central logic of the way multicellular groups evolve, the way groups of social insects evolve, and the way that societies evolve. Darwin very famously ended The Origin with this quote here, there is grandeur in this view of life, you've probably seen it before. The bit I like is he talks in this quote about how evolution has occurred as the planet has gone on cycling according to the fixed laws of gravity, and how cool and exciting to think that now we can say more than just the fixed laws of gravity, we can say also the laws of game theory and the principles of optimality as well. So I think that's us concluding. Thanks so much. Just say two things before we go. Paul and I are working on a project called Isaac Biology at the moment. Remember that. That logo took a long time to create, crossing out the word physics and putting the word biology next to it. So it does use the highly successful Isaac Physics platform. You already know that students from around the world use Isaac Physics, and excitingly, some interesting biological puzzles, sort of why don't animals have wheels? Why aren't plants black? Those sort of questions are going up on there now to be solved by school children around the world. And also, as just a shameless plug, if you sort of enjoyed today's presentation, part of my job at Homerton is I run a sort of weekly lecture series there. So you can't find out why you can't remember your childhood because that was a while ago. But tomorrow, if you want cheering up, are animals aware of their own mortality? Do they know they're going to die? How can we find that out? Yes, usually on Thursdays 5 till 6. But thanks so much for listening today. I really hope you enjoyed it.